Hello. Now, welcome to another lecture in the course. Today we're going to look at the exponential again. This time we're going to define it as a power series, or prove to, its power series. We could have used this as a definition, really. It's sort of the more proper complex analysis definition of the exponential. And this is the subsection 243 in the book. All right. So previously, some time ago, we defined the exponential using the real exponential and sine and cosine because we wanted quickly an exponential. And we didn't have power series yet. We did show that this this definition e to the z, this was or is holomorphic. It's complex differentiable everywhere, right? So let's do a different definition using power series. Well, not really a definition. It's going to be a proposition, right? But let's show that there is a different way to think about the exponential. So if we look at this power series over here, which you've probably seen, the power series for the exponential. So if we define a function using this, first, this is convergent, and it's the unique power series expanded at the origin. So we're expanding around the origin, such that at the origin we get f of 0 is 1, right? What the exponential should be. E to the 0 is supposed to be 1. And this function is its own derivative. We know that power series are complex differentiable. They're holomorphic. We can compute f prime. And so f prime is supposed to be the same thing, right? Now, moreover, the series actually converges, not just in some neighborhood of the origin. It converges in C. That's actually not hard to show. Just you compute the radius of convergence here, root test, ratio test. Your choice ratio test is the easiest. Okay, so the series converges, and it actually is the exponential. It equals the exponential everywhere. So let's prove this. So start with, let's just assume that we have a convergence power series that satisfies these guys, right? These two conditions. And let's show that it actually has to be this guy, that guy converges, and it will satisfy these conditions, and then we have to show that it actually equals the exponential. All right, so we start with an arbitrary convergent power series, and we apply these two conditions. So the first condition is fairly simple, sort of gives you one coefficient. So we know that C0, here it was just some unknown, but because f at 0 is 1, if I plug in f at 0, I just get C0, so C0 has to be 1, right? So we know one coefficient, right? Let's figure out if we can get all of them, right? So the other condition is that f prime is equal to f. So let's compute f prime, right? It's power series. We can differentiate it term by term, right? So I differentiate term by term. Okay, let's rewrite it as a power series so that it's it is a power series, but let's rewrite it as so that the powers are z to the n, right? So that we have this nice index here. So you change the index to write it in this form, and that has to equal f, right? F is just the original guy, right? Now, coefficients of a power series are unique. We've shown that, right? That means that the only way for this power series to equal this power series is for the coefficients to be equal, right? So we have this equation for the coefficients. And you just do a little bit of induction, starting with the fact that C0 is 1, right? And so, then you just basically have to keep dividing by higher and higher n. You get that Cn is 1 over n factorial. A simple exercise in induction, right? So we see that this power series, if there is a convergent power series that satisfies those two conditions, it has to look like this. And well, this series does converge in C again, using root test, ratio test, however you want to compute the convergence over here. Now, this this technique, you might have seen it before, right? I mean, this is the power series technique for solving differential equations, right? So this is something that you might have seen in your undergrad, and it's really, it's basically undetermined coefficient with lots and lots of coefficients, right? So usually, in an undergrad class, you don't really worry too much about proving things or showing conversions, but yeah, here, especially for this simple ODE, right? Yeah, it's simple. You can do similarly. You could define the series for sine, cosine, and all the other elementary functions. You can, if you figure out what the differential equation is, and it. As long as it's one of these functions that has a nice differential equation, then you can just you just solve it, all right? Solve it using power series techniques. That gives you the power series, and then you show that that thing converges, and you're good. Now, we haven't shown one other things. We haven't shown that this is actually the exponential, right? So we have to. I mean. It's sort of this that's sort of the uniqueness of the solutions of these ODEs, but without invoking Picard, right? Let's prove this explicitly. It's very easy for this particular equation over here, because we have that both f and the exponential, those are both holomorphic functions, so they're complex differentiable at every point, and they're equal to their complex derivatives. So let's divide them. The exponential is never zero, so f over the exponential, that's a nice holomorphic function everywhere, right? We can differentiate it with respect to z, so the complex differential. We write down the quotient rule, right? We're back in calculus, right? Now, over here, so that looks complicated, but notice that f and the exponential are equal to their derivatives. Therefore, this is f, this is just the exponential, so I have f times the exponential minus f times the exponential, and it's just 0, right? So this thing is constant. What does it mean? It means that f is some constant times the exponential, right? So we just need to figure out what that constant is. That's easy. You can again plug in that f at 0 is supposed to be 1 and exponential at 0 is supposed to be 1. So that constant had better be 1, right? Because it is supposed to hold for all z. Well, there we go. So that's it for this lecture. Next lecture, we're going to look at the identity theorem for analytic functions. So, basically saying that to know an analytic function, you just need to know it at enough points. Actually, countably many points is good enough, and you know the function, as long as it's the right countably many points. All right, so that's next time. So see you then.